Hello, it's GCSE Physics Explained. I'm going to take you through a triple physics paper. It is a paper 2 and it's the higher tier. And this paper was from Friday the 14th of June 2019. Question number 1. Figure 1 shows a paint sprayer. Some paint sprayers give the paint drops a positive charge as they leave the sprayer. The paint drops have a positive charge because the sprayer, does it remove electrons from the paint drops? Yes, removing electrons from the paint drops would leave the paint positively charged. If you were to add electrons to the paint drops, that would obviously make the paint negative because electrons are negative. Removes protons from the paint drops? No, that's impossible. The protons are kept inside the nucleus in the middle of the atom. It's only the electrons that are orbiting around the outside that can be removed. That's a mistake that a lot of students make. They say, oh well, the protons are positive, so if the paint has become positive, then it must be because it's added protons. I can see where you're coming from, but now that you know that the protons are kept in the nucleus in the middle and you can't get to them, then you know that that's wrong. So if something's positive, it's because the electrons have left. Part 2. Figure 2 shows the spray pattern from two different paint sprayers. So sprayer X, it's coming out linear. Sprayer Y, it's spreading out a lot more. Sprayer X does not charge the paint drops. Sprayer Y gives the paint drops a positive charge. Explain how charging the paint drops changes the spray of the spray pattern. 2 marks. Well, you can see that this spray pattern is wider. So 1 mark for saying sprayer Y is wider. And 1 mark for saying Y. Well, if these droplets are all positive, positive charges do not want to be next to other positive charges. So they repel away from each other. One mark for wider, 1 mark for repel. Part 3. Sprayer Y is used in a factory to paint a metal object. The object hangs by a metal wire that is connected to earth. Explain why a metal wire is used to connect the object to earth. Well, you don't want any charge building up. So if we use metal, metal is a conductor and it will discharge the object. One mark for conductor, 1 mark for discharged. The reason you don't want any charges to be built up on the object is that it could cause a spark, and if you're in a flammable area it could cause a fire. So if it was worth 3 marks, you could add that. Part B. Figure 3 shows 2 charged metal plates. The top plate has a negative electric charge, the bottom plate has a positive electric charge. On figure 3, draw the electric field lines between the 2 plates and show the direction of this electric field. Right, because these plates are flat and they are the same distance away from each other, you're going to end up getting a uniform field. So the first thing is that you'll end up with straight lines going from one plate to the other. That's for 1 mark. Which way does an electric field travel? It goes from positive to negative. So you get your 2nd mark for that. Question 2a. Which of these is the equation for work done? Work done equals force divided by distance? Nope. Work done equals force times by distance? Yep. That's why it's important for you to learn the equations. Part B. A ball has a mass of 0.046 kilograms, so that's our mass. Calculate the change in gravitational potential energy, so that's GPE, when the ball is lifted through a vertical height of that. That's our H value. Use this equation. So we just need to pop the values in. You've got to make sure that you know that gravity on Earth is 10 newtons for every kilogram. Got to make sure that the mass is in kilograms, and you've got to make sure that the height is in meters. And that equals 0.943. And all energy is measured in joules. Now we're okay putting it to 3 decimal places because they have got the mass to 3 decimal places. Part 2. The ball is released. Calculate the kinetic energy of the ball when the speed of the ball is 3.5 meters a second. So that's our V. Kinetic energy is question mark. Okay, so the equation for kinetic energy is a half mv squared. It's still the same ball from the last question. So the mass is the same as before. Now make sure that you square the 3.5 first. And that equals 0.28175. Part 3. The ball bounces several times. Figure 4 shows how the height of the ball above the floor changes with time. Use figure 4 to estimate the maximum height that the ball reaches after the first bounce. Okay, so here it comes. There's the height. As the time's ticking by, the height of the ball has fallen. There's the first bounce. The height that it gets to is about 0.9 meters. Part 4. Explain why the ball does not bounce back to its starting height of 2.05 meters. Well, the answer is always the same. It's lost energy. Now it's worth 2 marks, so see where the energy's gone. It goes to the surroundings. If it was worth 3 marks, you could say it's turned into sound. One mark, 2 marks. If it was worth 3, that's what you'd get for your 3rd mark. Question 3a. Which of these symbols is used to represent a thermistor in an electrical circuit? Well, I've got a lovely video that shows you all the electrical circuit symbols. Click the link above. It explains nice ways how to remember them. And a thermistor is D, this one here. Part B. The student investigates how the current in a lamp changes with the potential difference across the lamp. The student uses the results to calculate the resistance of the lamp. The results are shown in the table in figure 5. One value of resistance is missing from the table in figure 5. Calculate the value of resistance. So we're looking for the resistance. What has it told us? It's gave us the voltage and it's gave us the current. So V, I and R, we need to use Ohm's law. So that's V equals IR. Rearrange that to get R. I've got a nice video how to rearrange equations. It's called the magic triangle. Click the link above. Another nice way of rearranging equations is if you put a line under all of that and put a line under that. then when you move one thing from one side across the equal sign to the other side, it's got to cross the line. So we need to get resistance on the top, which it already is, and we need to get it by itself. So we need to take I over to this side, and then because it's came across to this side, it needs to go under the line down there. And I'll just rewrite that so it's nice. We're trying to work out that resistance, so we need to use that voltage and that current, and that equals 19.23 ohms. Now they haven't got any decimal places there, so we won't use any decimal places either, so that'll just round up to 19. Part 2. The student writes this conclusion: the resistance of the lamp is directly proportional to the potential difference. Resistance, potential difference. Comment on the student's conclusion. Use information from figure 5 in your answer. Right, so better refer to the data. So what do we generally spot? Why is he saying that? So the resistance is getting bigger and the voltage is getting bigger. Now if it's directly proportional, it means that if I was to double the voltage, it would double the resistance. So going from 1 doubled to 2, that has not doubled from 11 up to 22. It's only went up to 14. Let's look at that again. What if I say the voltage is 2? Let's double the voltage from 2 up to 4. Has it doubled the resistance from 14 up to 28? No, it has not. And also, directly proportional would mean if I was to treble the voltage, that would treble the resistance. So trebling from 1 to 3, has the resistance trebled from 11 to 33? No. Now, a lot of people miss out on the third mark because they don't refer to the information. So let's do that. Part 3. The student used a power supply that had fixed output voltage settings. Each of these outputs was a whole number of volts, so 1 volt, 2 volts, 3 volts. Describe how the student could add a component to the circuit that would provide a continuously variable voltage across the lamp. So not just 1 volt, 2 volt, but 1.1, 1.2, 1.3, so any value of voltage. Now we could do that by putting in a variable resistor, and variable resistors would go in series with the lamp. One mark for variable resistor, 1 mark for series. If it asked you to draw that, there's your battery, your variable resistor looks like that. There's your lamp. You'd obviously have your ammeter in as well over here, and you've got your voltmeter currently across the lamp. Now whatever voltage this battery is giving out, originally all the voltage was just going to the bulb, but now that I've put this in series, which it means one thing after the other with the bulb, now this will get some voltage and the bulb will get some voltage. So we could adjust the resistance of this, because how big the resistor is, that'll determine how much voltage it gets. So if we adjust the resistance of this, we can make the voltage on here bigger or smaller, and it'll make the voltage that's left bigger or smaller on this thing here. Question number 4, part A. Figure 6 shows 4 forces, P, Q, R and S, acting on a rod. The rod can rotate around an axle. There's the axle there. It's like a pivot point. Which force will make the rod rotate about the axle? You're looking for a force that's acting at right angles to the axle at a certain distance. So that's going to be Q. If you've ever adjusted a clock with a hand and you've got to put the clock forward an hour, it's got an axle, it's got a pivot point in the middle. If you try to make this hand move either this way or this way, you wouldn't be pushing there. You couldn't push there, and you couldn't push there either. You'd have to be pushing on the end here. I mean, you could push anywhere along there like that. Or if you wanted to push the clock forward, the hand forward, you'd be pushing there. So any of them would be good. Part B. Figure 7 shows a person trying to lift a large rock using a metal bar. So this is a lever. The rock weighs 1,800 newtons, so that's the weight. The person can only produce a downwards force of 600 newtons. So that's the effort force. This here would be the load force. The person cannot lift the rock. It weighs 1,800 newtons and they can only lift 600 newtons. So it's 3 times too heavy. Explain using calculations why the person cannot lift the rock. Now, this is to do with moments. This person pushing down here is creating an anti-clockwise moment, and this rock here is producing a clockwise moment. I always follow the force and go round the back of the pivot, and then that'll tell you whether it's clockwise or anti-clockwise. So that's clockwise. Now let's have a look at the moments. So the anti-clockwise moment of the person. So she's producing an anti-clockwise moment of 300 Newton meters. Now let's have a look at the clockwise moment of the rock. Right, well, she's not going to be able to lift the rock even using the lever, and that's because the clockwise moment of the rock is bigger than the anti-clockwise moment of the person. And that'll get you 3 marks. Part 2. Explain one change to the arrangement that will make it possible for this person to lift the rock. So we need to base our explanation on the calculation. So, in order to increase the moment of the person, she either needs to increase her force, but it says the person can only produce a downward force of 600 newtons, so that's not going to work. So we could get her to increase the distance. Look at all that extra rod that she's not using, the extra lever there. If she was to push further on the end, then that would increase the distance to the pivot, and that would increase her moment. What we could do is we could bring the rock in. If we could jam that lever under the rock more and bring that rock closer to the pivot, that would decrease the distance and that would decrease the moment of the rock. I thought I'd better add those in there. This would increase her moment, and doing this would decrease the rock's moment. Part C. Figure 8 shows a bicycle. The rider uses the pedals to make the large gear wheel turn. The large gear wheel moves the chain. The chain turns the small gear wheel. The large gear wheel has 48 teeth. The small gear wheel has 12 teeth. The large gear wheel turns 2 times each second. Calculate the number of times that the small gear wheel turns each second. Well, it's all to do with ratios. So if this has got 48 teeth, I'm not drawing them all, and the small one has only got 12 teeth, the teeth interlock 1 to 1. So every one of these teeth interlocks with one of those teeth. I know there's a big chain in between. I've got a nice video that'll explain things. You'll be able to click the link above once I've finished making that video. Now the large gear wheel is turning 2 times per second. So we need to work out the ratio of the sizes. So it's clear to see 48 teeth divided by 12 teeth. This large cog is 4 times bigger. So this thing is going to have to spin 4 times every time this large cog spins once. And if that's going round 2 times per second, that's going to go around 4 times faster, which is 8 times per second. Part 2. Oil is applied to the wheel of a bicycle at the point shown in figure 9, right on the axle. Explain how the oil improves the efficiency of the bicycle. Now, it's always best to base your explanation on the calculation, so let's have a look at the calculation for efficiency first. So efficiency equals useful energy out divided by total energy in. Now we also know that the total energy equals the useful energy out plus the wasted energy out. We often do that as a Sankey diagram. Now, oil is a lubricant, which means you're going to get less wasted energy. So if you get less wasted energy, it means you're going to get more useful energy. And if you get more useful energy, that means that the efficiency is going to increase. Now less energy will be wasted because there'll be less friction, because the oil is going to stop the surfaces from rubbing together quite so much. And that'll definitely get you the 3 marks. Now when I'm doing this walkthrough for these answers, I'm obviously telling you a lot more than what you need to use. I'm using these questions as an opportunity to teach you how to understand what's going on. In the exam you could probably get away with just saying oil is a lubricant, 1 mark, so there's less energy wasted for another mark. And then either say so more useful energy or say that the efficiency increases. You wouldn't have to put all of the equations and everything. It is good practice, and because I had loads of space, I thought I'd put those equations down as well for you. And what I've also got is I could even draw a Sankey diagram because I've got a little bit of room here, haven't I? So this would be your total energy in. This is your useful energy out. And this is your wasted energy out. So these two here have to equal that there. And that's called a Sankey diagram. Again, you wouldn't need to put that in this question. I'm just telling you about it, in case it's something you want to research yourself. Question 5. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.